Welcome back. So, now we come to another problem involving turbines, and this problem involves isentropic efficiency. It is a reasonably simple problem, but it involves the entropy production rate. So, let us just go ahead and read the problem. An adiabatic steam turbine handles 10 kilograms per second of steam. The inlet state is 10 bar and dry saturated. The exit pressure is 1 bar. The isentropic efficiency of the turbine is 0.8, and we have to determine the exit state, the power output and the entropy production rate. Of course, you notice that it is an adiabatic turbine, and hence Q dot is equal to 0 because it is given as such. So, let us go ahead and draw the turbine. This is I, and what do we have? It is 1 megapascal. This is because it is 10 bar. The HI is equal to 2777.1 kilojoule per kg. The inlet entropy is equal to 6.5850 kilojoule per kg Kelvin. So, these are quantities that we have directly picked up from the steam table by looking at 1 megapascal and its saturated dry state. So, now let us draw the HS diagram just to have a feel of what is happening. This is Pi and this is Pe. So, we can draw the inlet state and the so called exit state, which is ideal. So, once we get the exit ideal state, let us see how we will use the isentropic efficiency. So, this is I, and this straight down with the same entropy is E star as per our nomenclature. So, here at the exit we do not know the real state except what the pressure is. The pressure is given as 1 bar, which is 0.1 megapascal, but we will have to go ahead and calculate what the enthalpy and what the dryness fraction is. And how do we proceed? We first figure out what E star is. So, as far as E star is concerned, it is S E star is the same as Si, because this is the so called ideal process where the entropy at the exit is the same as the entropy at the inlet. This is not we get actually, but we have to go ahead and do this calculation. Once we get this, we can get X star, that is the dryness fraction assuming this. How do we get it? We use the entropy at Se star, which is 6.5850, and subtract Sf at 1 bar, which is 0.1 megapascal. From the tables we find it is 1.3028, and divide by Sfg, which turns out to be 6.0561, and hence we get this as 0.8722. Once we get X star, we can get He star, that is the exit enthalpy assuming the ideal process, and we know how to get it, which is just X times Hfg plus Hf, where Hfg and Hf are calculated at 1 bar. I will not do the calculation here, and we can get this as 2386.4 kilojoule per kg. Now, we know this is not the real exit state. We use the definition of the isentropic efficiency, and we know what it is. It is just Hi minus He upon Hi minus He star. So, we know that the real state would have been here E, and this difference here delta H real, let us say, would have been lesser than Hi minus He star. So, we get Hi minus He is the isentropic efficiency multiplied by Hi minus He star. So, we know what this is, Hi minus He star, because we know both Hi and He star, and we know that this has been given as 0.8. So, we can go ahead and calculate that Hi minus He should be equal to 312.56, which means that the real He should be 2464.54 kilojoule per kg, and this number should be greater than the ideal He star. So, it is greater. Now, what do? We calculate the real exit state and the real entropy at the exit. So, let us just proceed to do that. So, x at the exit is equal to 2464.54. So, we use He here, minus 417.5, we use Hf at 0.1 megapascal, divided by 2257.4, which is Hfg. So, we write down the answer for it. I will just do it directly. It is 0.9068, and we realize that this is drier than the state which we would have achieved ideally, and of course, the process was even more irreversible. You would have probably got an even drier state. So, we know what the real exit state is now. Now, it is reasonably easy to get Se, because all we have to do is use x multiplied by Sfg plus Sf, where Sfg and Sf are calculated at 0.1 megapascal, and we get that as 6.7945 kilojoule per kg Kelvin. So, it is easy now. We write the first law, steady state, Q dot minus W dot S is equal to m dot He minus Hi plus Ve squared by 2 minus Vi squared by 2 plus Gze minus Zi. Now, notice that nothing has been said about the inlet and exit velocities and the difference in heights, and we have already discussed this much earlier when we were solving our second problem, that it is a reasonably good assumption to put these quantities as 0, because they are reasonably negligible compared to the delta H's that we get. So, we put this as nearly equal to 0, nearly equal to 0, and we have been given it is an adiabatic turbine. There is no harm in then putting Q dot is equal to 0, and then we get W dot S is nothing but m dot Hi minus He. We have transposed the negative term here, and it is reasonably simple, 10 kilograms per second multiplied by 312.56 kilojoule per kg. This is equal to 3125.6 kilojoule per second. Of course, this unit is also kilowatt. What about the entropy production rate? We realize that the second law, when we wrote it, it would have been m dot Se minus Si is equal to Q dot by T plus S dot P, where S dot P is greater than equal to 0. It is adiabatic, this is 0. So, what we have is S dot P is nothing but m dot Se minus Si, and this is 10 kilograms per second, and we multiply it by the difference between Se and Si. So, Se is now 6.7945 as per our calculation, and Si is 6.5850, and the units for these are kilojoule per kg Kelvin. So, we can remove the kg. Kilojoule per second is nothing but kilowatt. We multiply this and get S dot P is 2.095 kilowatt per Kelvin. So, this is our entropy production rate. This is because the turbine is not really isentropic. it is not going to its ideal state, there are irreversibilities in the turbine, it comes out as a drier state, and it also means that the exit entropy is higher than the inlet entropy, and we can easily calculate the entropy production rate. Right now the S dot P is not really useful, but we at least go ahead and calculate it. What really is important is we know the exit state, and we can go ahead and finish our calculation as to what the real work output is, which is what we have done. Thank you.